This video will demonstrate the proper technique on how to determine the boiling point of a liquid sample. The determination of a boiling point of a liquid sample can lead to the characterization of an unknown sample by comparing its experimental boiling point to known literature values. In this lab, you will have to determine the identity of an unknown liquid sample by comparing your experimental boiling point to a list of possible compounds as well as their literature boiling points. Boiling point is defined as the temperature at which the liquid and gaseous phases of a compound are in equilibrium. In an ideal case, the boiling point would be a single temperature, though the actual boiling point is likely going to be a small range of temperatures. When a compound is in its liquid phase, there are sufficient intermolecular forces between the molecules to keep the compound as a liquid. As the temperature increases, the kinetic energy increases as well, and the intermolecular forces are lessened to the point that they no longer hold the compound together as a liquid, and the compound will vaporize. The boiling points of different compounds will vary according to the strengths of the intermolecular forces as well as molecular size. The main intermolecular forces listed from greatest to least are ionic forces, which occurs between two ions, hydrogen bonding, which occurs between a hydrogen and either nitrogen, oxygen, or fluorine, dipole-dipole interactions, which occurs between two dipoles, and London dispersion forces, which occurs between two non-polar molecules and are due to the motion of electrons within molecules, leading to temporary dipole moments. The more these interactions are present between molecules in a compound, the stronger the intermolecular forces, the higher the kinetic energy needed to become gaseous, and finally, the higher the boiling point. Consider similarly sized hexane and hexanol. What are the intermolecular interactions in hexane? What are the intermolecular interactions in hexanol? Which compound will have a higher boiling point? Since hexanol has more intermolecular forces than hexane, hexanol will have a higher boiling point. Boiling a beaker of the compound would allow for a very rough and inaccurate boiling point determination. It is exceptionally difficult to determine the temperature to which the boiling started. In order to perform a boiling point determination, you're going to need a Theile tube filled with oil attached to a retort stand with a clamp. Notice that the regular green plastic finger protectors have been replaced with a more heat-resistant finger protector. This will already be set up for you when you come into lab. So besides that, you will need a Bunsen burner, a mercury thermometer, pasture pipette, your sample. You will need the small test tube specifically for boiling point, a capillary tube with one side fused, Bunsen burner lighter, a rubber stopper with a hole drilled in the center, and a little rubber O-ring. To set up your apparatus, first take your thermometer and your rubber stopper and put the rubber stopper onto the thermometer. Be careful when you're doing this as to not snap the mercury thermometer. Okay. Once it's on there, take your small test tube and your rubber O-ring. Line the bottom of the two up and connect them with the O-ring. Line the O-ring up close to the top. Now the test tube is in line with the bottom of the thermometer. Your next step is going to be to add your sample into the small test tube. You're only going to need about 1 centimeter of liquid, and that corresponds to about as much liquid as there is mercury inside of the bulb of the thermometer. Take your pasture pipette and fill up your test tube. You're now going to take your capillary tube with one side fused and submerge the open end into your small test tube. Okay? So right now the open end of the capillary is going inside of the test tube. This is now going to be referred to as your bell tube. The test tube thermometer unit can then be lowered into the oil. First, lower your stopper Lower the test tube into the oil so that all of your liquid sample is submerged in the oil, but the oil is not touching your rubber O-ring. This will take some fiddling. If the hot oil touches the rubber O-ring, it could cause it to snap, which would then make your test tube drop, and this could damage the equipment. So now the liquid is completely submerged in the oil, but the oil is not touching the rubber O-ring. The setup is now finished, and you may begin the boiling point determination. I understand that many of you do not have a lot of experience working with a Bunsen burner. I'm now just going to take a few moments to talk about some of the key features on a Bunsen burner, as well as methods for safe handling. If you feel comfortable with the Bunsen burner, please forward to this part of the video. There are two main dials or valves on the Bunsen burner that you should be familiar with. There's one on the bottom and there's a big one on the top here. The one on the bottom is going to be your propane flow control dial. It follows the rule righty-tighty, lefty-loosey. So even though it can open very far, just less than a quarter turn is more than sufficient to get enough propane flowing for your combustion. Okay? So that orientation is closed, quarter turn to get enough propane flowing. Okay? This other valve here is much larger, it's this entire part here, and this is your oxygen control valve. This will allow oxygen to enter into your combustion chamber. A blue flame represents complete combustion and a red flame represents incomplete combustion. For this experiment, as well as most others, a blue flame is desired. So turn your oxygen control valve until you see a nice blue flame. This is a Bunsen burner lighter. Its job is to make a spark which will ignite the flow of propane from the Bunsen burner. To make a spark, squeeze the lighter. There has to be a lot of friction between the flint and the steel ribbon, so make sure you are also pushing them together. Pushing down and squeezing may be a little awkward at first, so practice making a spark with the lighter before the fuel is flowing. Before you light the Bunsen burner in the fume hood, ensure to remove any flammable materials. Now you're ready to ignite the Bunsen burner inside of the fume hood. Okay. Your gas outlet is located right here. So the tap on the outside is labeled gas, and it's the top one, so your top outlet is going to be your gas outlet. So you're going to attach your rubber tubing to the gas outlet. Okay. You're going to ensure that the propane flow dial on your Bunsen burner is closed. And then you're going to turn on the gas valve. Okay. Then going to do a quarter turn and open your propane flow. Take your Bunsen burner and ignite the flame. Here I am adjusting the oxygen flow valve to ensure that the flame is blue. Fan the flame over the lower arm of the Theile tube. The Theile tube is made so that the heat will convect through the tube and all of the oil will be the same temperature. It is desirable to have a slow heating. As you are heating the system, watch the bottom of the bell tube. You will be looking for bubbles to evolve from the bottom of the bell tube. This will signify the point at which the pressure in the bell tube is greater than the atmospheric pressure, which is due to the sample boiling. You will want to record this temperature, at which you first see a steady stream of bubbles coming from the bell tube. This is not the temperature you will use to determine your unknown, but it will give you a better idea of the temperature to record in the following steps. Once you record this temperature, stop heating. You will likely notice some bubbles evolving from the tube well before the boiling point of the sample. This is because as the temperature increases, the volume of the gas within the bell tube will expand and some will escape. Do not write this temperature down. Wait until there is a fast, steady stream of bubbles. Continue watching the bell tube so that you may record the temperature to which you first observe the liquid going up the bell tube. The system has now cooled back down to the boiling point, so the sample vapor inside the bell tube is condensing back into a liquid. Because the condensed liquid phase has more than 100 times smaller volume than the gas phase, the huge decrease in volume creates a vacuum suction in the bell tube that pulls up the sample liquid to fill the void and equalize the pressure. Once you have recorded this temperature, wait until the temperature to fall a few degrees below. Once that temperature is reached, begin to heat the system again by the same method as before, but at a slower rate. Hold the flame further away from the tube to accomplish a slow heating, this time paying especially close attention to the bell tube around the temperatures to which you previously recorded. When you first observe a steady stream of bubbles from the bell tube, record this value. It should be within 1 or 2 degrees of the second temperature you recorded. As stated at the beginning of this video, the boiling point of a particular compound will be constant under the same atmospheric pressure. As you increase in altitude, the atmospheric pressure will decrease. Displayed here is the approximate relationship between altitude and pressure, as well as some reference points. As the pressure decreases, the boiling point will decrease as well. For example, water will boil at 96 degrees in Calgary. Most literature boiling points will have been corrected to sea level. In order to compare the boiling point you recorded to the literature boiling point, you may have to add in a correction factor depending on the altitude to which you took the measurement. The correction factors can be determined by this equation. Although Toronto is not high enough in altitude to have a significant effect, changes in weather may significantly change the pressure and alter your results. A barometer is available to record the pressure in the lab. For this lab, your instructor will make the measurement for you. To recap, in order to take a boiling point, heat your sample by heating the oil which it is submerged in by slowly fanning a flame over the Theile tube arm. Record a first temperature at which a steady stream of bubbles begins to elude from the bell tube. Stop heating and allow to cool. Record a second temperature at which the liquid just begins to enter the bell tube and allow to cool a few degrees below this temperature. Resume heating of the tube, but this time at a slower rate than the first heating. Record a third temperature to which a steady stream of bubbles begins to evolve from the bell tube. Compare the second and third values to the literature values of your possible unknowns to determine the identity of the unknown.